In this video, we are going to describe the Cantor distribution, which has no PMF and no PDF. So it is a little difficult to describe this distribution. We shall describe it using its CDF. Now the problem is even the CDF, which of course exists, cannot be described very easily. What we shall do is we shall construct a sequence Fn where each Fn is some CDF, and we shall show that these Fn's will converge to a function pointwise. In fact, the convergence will be uniform, and then show that this f, which is defined as the limit of Fn, is actually a CDF, and that will be the CDF we are looking for. So the way I am going to describe this distribution is pretty roundabout. First, think carefully about the entire process before we start doing it. Now, before we get into the mathematics, I will show the entire thing pictorially. To understand it pictorially, we shall start with the unit interval. And then what I will do is I will take the middle 1/3 and I shall erase the middle open 1/3. So I keep the point 1/3 and 2/3 themselves. As a result, now I am left with two closed intervals. 1/3 is still there, 2/3 is still there, but everything in between this open interval has been deleted. Now I shall do the same thing with both these two intervals. I shall consider their middle 1/3 portion and delete the open middle 1/3 here as well as there. So after this second step, I am left with four intervals like this. They are all of equal length. You can understand what I am going to do next. I will now delete the middle 1/3 of each of these four intervals, and now after three steps I will be left with 8 intervals all of equal length, and after n steps I will be left with 2 to the power n closed intervals. I am always deleting the open, central open part, so I am left with closed intervals. I shall give this a name. I will call this S3. So 3 because I have done 3 steps of deletion. So the initial thing S0 was the complete unit interval. S3 consists of 2 to the power 3 closed intervals. Now I plan to define my distribution functions Fn as I had suggested. Fn is the distribution function for the uniform distribution over Sn. It will help if we just draw graphs of the first few f's. Let's start with F0. F0 is the CDF of the uniform distribution over 0, 1. So it is like the 45-degree line. 0 here, 45-degree line, then again flat here. Now we go to F2. For this I do that deletion thing. Now I am uniform over these two intervals. So half probability here, half probability here, uniformly distributed, no probability here. As a result, the distribution function will look like straight jumping up to half, then remaining flat, and then again straight jumping up to 1. Now my picture is not drawn very nicely, so this line should actually be right at the center. So this triangle should be just a reflection of that triangle, but my picture is not that nice. So this one is my F1. Now let's move over to F2. For this I will again delete the middle portions, and as a result I will have more flat regions. So F2 will look like this. 0, you jump to 1/4. So each of these things has 1/4 probability. Flat, again make another 1/4 jump, not jump, so this is just going up like a ramp, there is no discontinuity. Then again flat, again a ramp of height 1/4, flat, ramp of height 1/4, and you hit 1. So you understand, as you move from each fn to fn plus 1, you are basically taking one of these slant things and replacing it by a zigzag. So it should be graphically obvious that all these functions are getting closer and closer and closer and closer. So f1 differs from f0 a lot, but f2 differs from f1 less and less and less. To understand this, I will make this picture bigger. Here I have shown a typical slant part of the graph of fn. So I am zoomed in on only one slant part. By the property of fn, there are 2 to the power n many such little parts, each accounting for probability 2 to the power minus n. Now when we move from fn to fn plus 1, that looks like this, where the flat parts are still remaining, because once you delete some region, you are never bringing it back, but this extra flat part is added, so this height is half of that and this is another half of that. So you see, whatever difference of fn plus 1 and fn there is, it must be all confined within 2 to the power minus n. And whenever you take any future step like this, everything is happening inside that 2 to the power minus n. So if you move from fn to fn plus k, then this absolute difference is always bound to be less than 2 to the power minus n, which fortunately is free of both x as well as k. And this will be the key to the proof for uniform convergence that we shall take up in the next video. In this exercise, you are required to show that the slope of each slant part of fn, in this case I am showing f2, so this is a slant part and this is a slant part, they are parallel, that slope will be 3 by 2 to the power n. As a result, as n goes to infinity, these will go to infinity, so these things are getting more and more vertical.